So in this video we will do some calculation and related to thermodynamics, and here is this comparison between the equilibrium constant and thermo value. If we multiply, in case of equilibrium, basically we raise the power k to the constant, and in case of thermodynamic value, delta H, delta S, delta G, we multiply the value by the same constant. And if we are reversing a reaction, we reverse the sign of the value in thermodynamics, but in case of equilibrium constant, or basically we take the reciprocal of the k. And if we are going to add the two reactions together, we add the delta H or delta S, delta G values with their sign, but in case of equilibrium constant we multiply. So this is the simple rule we have to follow when we do any math calculation on the equation. So first slide will be related to calculation will be this much. This will be where we see that appendix C has a value of, so in your book it will be provided the delta H enthalpy formation, standard enthalpy formation, standard Gibbs free energy formation, and standard entropy will be provided through the table. And in the current book usually they are in appendix C at the back side, and also the table 19.1 has a standard entropy value. Use the equivalent of Hess's law. If you remember the thermochemistry from previous chapter, we already have studied the Hess's law. We will use that one, and use the equation on the slide 31 and 33. So basically this is the most common equation we are going to use, and but we will do some other equation, we will use some other equation as well. So first question is this one, that example delta H, standard condition, delta S and delta G for this reaction is given here, and what they are asking, basically they are asking that calculate the carried out at 25 degrees Celsius 1 atmosphere. It means we are talking about we are talking about the standard condition. Calculate delta H, delta S and delta G using the following data, right? So, and for oxygen it is not given, but here you can see delta H of formation of, this is pure oxygen, is in elemental form, and if it is in elemental form, so the value will be 0. So this is the one thing which we have to figure it out, and then how we are going to use the formula. If you remember that delta G in standard condition will be equal to delta H standard condition minus T delta S, right? So this is the one formula which we will use, and another formulas, if you remember that we were using delta H formation for this one, product minus reactant, for delta S product minus reactant, and for delta G product minus reactant. So these are the formula we are going to use here. So let's start first to calculate the delta H for this reaction, and delta H for this reaction will be number of moles of the product side and number of moles on the reactant side. For the SO3 and the reactant side will be 2SO2 plus O2, right? And here you can see total number of moles on the product side is 2 moles, and in case of reactant we have 2 mole and 1 mole, total 3 mole. So 2 moles of the product of SO3 and delta H for SO3 is given minus 395.2 kilojoule per mole, and delta H, so this was the product and that's it. And for reactant, 2 mole multiplied by enthalpy of SO2, which is minus 296.9 kilojoule per mole, plus oxygen. So oxygen enthalpy is 0 for 1 mole, so it's already gone from the calculation. Now we can just simply calculate by multiplication of this one and then multiply by this value and then subtract. So once we subtract, we will get the delta H value is minus 196.6 kilojoule, and 1 mole will also be cancelled out. So basically this will be exothermic reaction because delta H is the negative sign. Let's calculate the delta S for this reaction. Delta S will be exactly same, product minus reactant, 2 moles multiplied by reactant, product is 256.2 joule per Kelvin per mole minus 2 multiplied by SO2 and then plus 1 mole of oxygen. Now once we will do calculation for this one, multiply and then subtract for this one. Basically we have to add these two together values for reactants, and we'll get the delta S for this reaction is minus 190.0 joule per Kelvin, and so here you can see this, and if we want to present in the kilojoules, basically we have to divide by 1000, so it will be minus 0.19 kilojoule per mole. And the important thing is this, in this is the negative sign for the entropy. It means losing entropy, more order system, right? So once this reaction is going on from the reactant to product, we are losing the entropy, and even then you can see here the 3 mole, here is 1 mole and 2 mole, so product have less entropy. That is why we got the negative sign. Next we have to calculate delta G. So delta G values for free energy is not given in the table, so you can see there is no table for delta G. That is why we will utilize the delta H and delta S value, which is already given in the, we have already calculated. And temperature is for a standard condition, which is 298 Kelvin. So delta H value I replace here minus temperature and delta S. So why I why I converted into kilojoule? Now you can understand that because here the value is already in the kilojoule for delta H. So once we will get the value from the math calculation, we will get this, delta G will be minus 139.9 kilojoule, and the negative sign will shows that the reaction will be spontaneous reaction. So this was the one question example, and then we'll see a few more examples, and one is here, and this says that use data from the appendix to calculate the delta G for the combustion of methane. So for this reaction we have to write the combustion of methane first. So methane gas is CH4 plus 2 oxygen gives out CO2 plus 2 H2O. So you have to make sure the reaction is balanced. 1 carbon, 4 hydrogen this side, 4 oxygen, and 2 4 oxygen. So reaction is balanced now. And then delta G, how we are going to calculate? So appendix C, we are going to use product free energy in the standard condition, and okay, reactant free energy in the standard condition from the table. So table is not shown here, but I already extract the value from there. But we know that 1 mole of methane gas, sorry, this is the reactant. So here we have to write down first carbon dioxide gas. These are the product. So 1 mole of the carbon dioxide gas multiplied by its delta G, its G free energy, and then plus 2 moles of water multiplied by free energy of water, then minus moles of reactant. So 1 mole of methane gas multiplied by its G, and then plus 2 moles of oxygen multiplied by G. So G for this oxygen is 0, elemental form. If any element is in the pure element form, basically it's delta G and delta H, both will be 0, right? So once you will solve this math, we will end up this delta G is equal to minus 800 plus 800.7 kilojoule. So this you can see again here, this is the delta is negative standard delta G. It means this reaction is spontaneous. And so this was the second example, and let's see a few more examples, and these are a little different than the earlier one. The heat of the fusion of polyethylene is approximately 7.7 kilojoule per mole. So heat of fusion, basically H fusion is given here, and the corresponding entropy means for this reaction entropy is value is given. The data, use these data to estimate the melting point of the polyethylene. So melting point temperature they are asking. So if you remember this equation, delta G is equal to delta H minus T delta A, T and delta S, and for a spontaneous reaction, basically this reaction is a spontaneous reaction, that is why delta G will be 0 here. And we can utilize this reaction. So what will happen here, basically delta S, we can rearrange this equation. It will become like this one, that delta S of surrounding means entropy change in the surrounding will be equal to minus delta H of system divided by T of system. So here temperature will be, which is a melting point, will be equal to minus delta H divided by delta S, and the value is already given, delta S, delta H value, heat of fusion is already given 7.7 kilojoule per mole, and then entropy is given 19 joule. So but we have to convert this 19 joule into kilojoule. So basically we have to divide, or we can multiply on the top. Then we can cancel out the common units, and then we'll end up the temperature for the in the Kelvin. So this so the melting point for this polyethylene will be 405 degree Kelvin, or if we subtract from 273, we will get the degree Celsius value in the melting point. So this is the another example, another variation in the example. Let's see one more example. Confirm that the reaction below would be spontaneous by calculating the standard free energy change using a value from the table 10.3. So here we are not showing the table, but let's calculate this. So delta G of standard condition we have to calculate for this reaction, and for this reaction will be equal to product delta G minus reactant delta G. Basically free energy formation of product minus total free energy formation of reactant. And what else they are saying here, confirm that the reaction would be spontaneous. Spontaneous means delta S must be negative, and okay, so let's calculate these values. So this product is only one product, C4H10, and based on the table, so there is 1 mole multiplied by 115.71 and then minus 2 moles of the C2H4 multiplied by its value, and delta G for the hydrogen, which is again elemental form, will be 0. So the simple math, we have to multiply and then subtract. So basically when there are two negatives, so they will add up together. Delta G will be equal to 251.95. Since delta G is negative, indicate that this reaction would be spontaneous under standard conditions. So this was the another example of calculation of thermodynamic value, and you can solve some more questions to understand other examples.